Ok lắm.
Okay, so in the last technical session, I'm gonna introduce you to an extension of the whole thing that I've just been talking about. Okay? So this is the slide that I want to show you. I wanted to show you immediately, but then I realized that it wouldn't make any sense to do without knowing the previous two sessions. So this is the categorization of the whole thing I'm going to talk about, and compare it and put it into the space of the whole machine learning, reinforcement learning thing. So if you think about the environment where the agents need to behave, need to perform, if the environment is more like a stochastic thing, then there's been a lot of work done in control theory, for example, 100 years of research there, not 100, 60, 70. Reinforcement learning is also very hot, very mainstream topic in machine learning. It also deals a lot with this stochastic behavior. The stochastic Martian bandit or the stochastic bandit literature kind of like lies between the intersection of the two. So it's half reinforcement learning in the sense that if you think of you're familiar with reinforcement learning, you can think about MDP, right? Multiple decision process. So in multiple decision processes, you make an action, you move the system from one state to another one. Martian bandits, they don't have state, so it could be seen as classical stochastic bandits. You can regard them as a stateless MDP, stateless reinforcement learning model. It is also a control theory because whatever you do, you have a feedback, and then you need to adjust your model to make sure you come up with the best policy. But the second session, the adversarial bandits, they move away from this stochastic environment. So because of this, they're not really reinforcement learning anymore. And I know we had a discussion earlier. The bandit theory, whether bandit theory leads to reinforcement learning or this special case, it's not really because of this. We are looking at all the cases as well. And because of this adversarial setting, now we can expand it to something much bigger, which we call online adversarial optimization. And this is the focus of the last session, this session. Okay, so the reason people nowadays in our community move away from stochastic behavior, they still do a lot of research on that. But the more theoretical people or the more focused on adversarial setting is because the following. So you can prove that any regret you achieve in the adversarial setting, remember the external regret, you can directly prove that if you put everything into a stochastic setting, you either get a state regret or smaller. This is a very simple argument. It's like a max of the expectation and expectation of the max function. It's a form A function. So one is so the max expectation will be larger than the expectation of max. So implication of this one is that if we focus more on adversarial setting, which is much richer, then actually we can also behave very well in the stochastic setting. So we don't need to always look at it. Okay? And this kind of like has this kind of claim or this kind of implication has driven people to look at the adversarial setting instead. And they started expanding the model of the Martian bandits into something they call later as online optimization. And the way we can expand is of course. So in this model, in this generalized model, each time step, instead of choosing the value for the arm, now the operator, what they can do with it, is the classical bandit, right? This is the classical bandit. So in classical bandit, what it does is that it chooses a value for each arm. So in the adversarial setting, this value is arbitrarily chosen. If this is a classical superstick, then this value is not arbitrarily chosen, but is drawn from a distribution. In the adversarial setting, adversarial online optimization world, now the whole thing is transferred, it can be translated into tutorial. So now the action space is not finite arms anymore. It's not arm 1, arm 2, arm k. It can be anything. It can be continuous space. It can be compact. And when you choose action, you choose a point on that space. Okay? For example, it can be anything. You can think about anything. It doesn't have to have a metric space. It doesn't have anything. Whatever you want. Right? Then, based on that, the opponent now, instead of choosing a value to each of the points, what he does is that he chooses a function on the set of the search space, of the action space. Okay? That function can be anything. And then the player comes and now says, okay, I'm going to choose one element of the search space, 1 point, for example, and I want to see the value of the function at that point. That would be the reward. Okay? That would be the reward. And now the goal is to minimize the regret or minimize this, maximize this term. So minimize this term. This is the best fix in hindsight. We still have the best fix in hindsight. Minus our performance or the rewards we have achieved. Okay? So that's all what we want to do. Okay? But now the difference is that instead of like assigning values to the arms, what we have is a search space which has any shape. And the value is the value, now we have a function. So the opponent will choose a function, and then we look at one single value of that function. Okay, is it clear? That's why it's called optimization instead of management. So, so this is it. So now the question is, how can we do no regret? How can we design no regret algorithm in this case? Answer is going to be in the next slide. It's not going to be easy. You're not going to like it. But before that, we have to look at the way we can gather information. So until now, because in the bandit setting, we only care about arms. So we pull an arm, we see a value. Okay? We don't care about the rest. But now, because the system is coupled by a function, so that function might have correlations. Okay? So now we can say that we are seeing one point, but we can see the whole function. So the feedback now can be much richer. So now we have the case of full information. Feedback means that at the end of the round, the opponent chooses a function, I choose a point. Instead of just seeing the value of that point, of the function at that point, now I can see the whole function. Right? But I only get the value at that point. So the reward for me